Good afternoon, everyone, and welcome to another of our virtual tours of outer space. My name is Josh. I get to be your pilot on our show today, but for today, I would say you all watching are our captains because you get to decide where our imaginary spaceship flies today. Sounds like we already have some suggestions. Someone's seen this before. Sandhya suggests Jupiter. If you've got another place that you would like to visit, just like Sandhya did, throw it in the comments. We're on Facebook, from YouTube, we get to see both. And we are delighted to take suggestions from you on where we go on our virtual tour today. We are able to do this tour because we are using the OpenSpace software. OpenSpace is a very cool program, and especially a cool one because it's one that I can use to fly you around the solar system, and it's one you can use at home. So if you are excited by what you saw today and you are dying to check this out for yourself, by all means do so. Download it, check it out, play around with it, get involved, and let us know what you think. When we're flying around in a software like this, we get to see actual science imagery represented digitally. So last week we had some folks commenting about how they thought this was weird that we were showing you so much computer generated imagery. Well, I'm here to tell you we are not showing you computer generated imagery. This was never dreamed up by an artist. This is actual NASA imagery that we've put on a round thing for you to check out. We are currently looking at the planet Mercury. Mercury is a super cool world to look at because of that panoply of craters all across the surface. They are overlapping, they are interacting with each other, they are changing the Mercury in a beautiful and compelling way. But we got a request for not Mercury, the smallest of our planets in a rocky world, but kind of the opposite end of our planetary spectrum. Let's go check out Jupiter. So Jupiter for sure is not the smallest planet in our solar system. It is the biggest planet in our solar system. It is not a gaseous world covered with craters, a rocky world covered with craters. It is a gas world. It's currently not cooperating with me. Hold on one second. Let's see if we can get Jupiter to show up. Seems like Jupiter is not cooperating. When we look at Jupiter up close, though, we should expect to see not a uniform gray surface, but a striped surface, one with interacting cloud bands and especially that great red spot. Jupiter is a beautiful world to check out. Trust me on that. We might have to reboot before we get it to work. But Jupiter is a really awesome spot, completely devoid of craters. Craters are a really useful thing for us to use in our solar system because when we look at a crater, we are able to determine the history of an object. Rocky surfaces record their past. Gas giants really don't. So there's a much bigger gulf of history laid out on a rocky world like Mercury than a gaseous world like Jupiter. So when we want to learn about Jupiter and its relationship to the rest of our solar system, we actually sent a probe down into the clouds of Jupiter to scoop up some of that material. That was dropped by the Galileo mission, I think back in the 90s. And it was able to show us that the composition, the ratio of hydrogen to deuterium inside Jupiter very closely matched what was predicted based on our theories of the evolution of our universe up until that point. Jupiter was sort of a time capsule that had preserved evidence from 4.6 billion years ago. When you look at the stars that make up the area around us, we're showing you a beautiful slice of the Milky Way. I think we had a request from Josh, good name, to check out the Milky Way, center of the Milky Way. Two of my favorite things, the name Josh and the center of our Milky Way. You can actually see it right over here. How do I know that's the center of the Milky Way? Why am I just pointing you in a random direction, telling you it's the center? That's a tricky thing to answer. But we can actually see a very cool asterism, a shape in the stars right here. It's a little funky looking because we're seeing it upside down, but remember there is no upside down in space. Especially this would be, I guess, our southern hemisphere version of this asterism. You can see what's called the teapot. Now look carefully. I can see one star right here, two stars, three stars that make a nice little triangle. There's four stars right here that make a little shape we call the handle. And then over here, I can see one, two, three bright stars that make the spout. So if you connect all these dots, you've got the spout over here, the handle right here, and the top of our teapot. This would be the bottom, the flat surface it rests on. Well, that's telling us that Sagittarius is these bright stars, and the center of our Milky Way is right over there. Now, if we were to fly into the center of our Milky Way, we would see a super interesting object called Sagittarius A star. That's a supermassive black hole that we've charted at the center of our galaxy. You might be thinking, Josh, how can we see a black hole at the center of our galaxy? You can't really see a black hole. That's one of the reasons they're so interesting to study. A black hole is a very massive object, so massive, in fact, that light can't escape its gravitational influence. So, how do we know it's there? We've watched stars orbiting it. We've watched stars orbiting it at incredible speed. The only thing that could make them move that fast would be something very heavy, something very small so that they don't bump into it, and something that shines no light, or else we'd see that object. So, what's heavy, dense, and shines no light? A black hole. And based on the mass estimates, we are talking about something that is millions of times the mass of the sun. That is a supermassive black hole. But this is not a supermassive black hole. This is a very bright object in our own solar system. Its cloudy banded surface looks a little bit like Jupiter, but I'll tell you this for free, isn't. This is actually a planet that has a lot more in common with Earth. Which planet is it? Well, if you've got a guess, throw it in the comments. This is our next door neighbor planet, sometimes called the sister of planet Earth, or our twin. This is, of course, Venus. So when we think about Venus, the surface that comes to mind is usually that cloudy surface, but the actual rocky surface looks a little bit more Earth-like. And when I say Earth-like, I mean a terrestrial rocky world, not necessarily one that looks a lot like our own planet. So Earth-like for astronomers sometimes doesn't mean like Earth. It means a rocky terrestrial world. Doesn't have to be a perfect match, doesn't have to have water, doesn't have to have continents like we see. When we look at something like this, we are seeing an object that has a shared history, kind of a commonality with our planet. We were probably born at around the same time, in the same part of our solar system, so we evolved similarly. However, at some point, Venus had a runaway greenhouse effect, making the surface get hotter and hotter and hotter due to buildup of carbon in its atmosphere. So when we look at this planet, we are talking about a surface hot enough to melt lead. Not at all a comfortable place for you and me, but nonetheless an Earth-like planet. So the next time you hear an astronomer say, we've discovered an Earth-like planet just a few solar systems away, don't believe it. Well, they did discover an Earth-like planet, but this is not a place where humans could go hang out. It would be a pretty inhospitable environment, overwhelmingly. We have yet to find a planet that is a close enough match for planet Earth that we think humans could exist on it. Some life is a lot tougher than humans, so there are some worlds that we think maybe human beings could survive on, or excuse me, life could survive on. But for human beings, we're a bunch of wimps. We like our temperatures somewhere between melting lead and absolutely freezing. So, well, it would be a lot harder to find a home for us. Okay, looks like we had some suggestions. How big is our black hole? So that's always a tough thing to define with black holes. I think its mass is around 4 million solar masses, but I would want to double check that number. I'm remembering 4 million and 20 million, which is pretty far apart, but in terms of astronomy, they're within an order of magnitude. One of them is our supermassive black hole's mass. The other one is maybe our next door neighbor's supermassive black hole, but I would want to double check those numbers. But I'm guessing it's either 4 million or 200 million solar masses. So, the last point for that is how big does that make it? We usually measure a black hole by the size of the event horizon. That means how far out is the distance light can't escape at, and I think that would fall within the size of our solar system. I think it's around the orbit of one of the ice giants, either Uranus or Neptune. So if you crammed millions of suns within the orbit of Neptune, that's the kind of mass we're talking about when we talk about a supermassive black hole. But I would want to double check all those numbers. If you leave that comment on there, I will do my very best to follow back and give you researched answers instead of what I kind of remember from a test 8 years ago. So we had another question pop up. Asteroids. Ooh, good idea. So let's check out some asteroids. Now, I know we have one asteroid in system. I just saw some more errors pop up. Let's see if we can get to it. I'm going to take us in to an area between the orbits of Mars and Jupiter, an area commonly referred to as the asteroid belt. Once upon a time, people thought that the asteroid belt was going to be a planet that never formed, maybe a mysterious lost world. Uh-oh, the error was that it's not even taking us to Ceres. This is Venus again. So the problem was when you add up all the stuff that makes up the asteroid belt, there really isn't that much of it. If we look at the entire area between Mars, which is right over here, let me turn on Mars's orbits. Showing. You can see right about where Earth is. We're the nice blue orbit. The gray one is Mercury, yellowy orange is Venus, and bright red is Mars. You can see between Mars and much farther out, Jupiter, there's kind of a weird gap. Well, we thought that a long time ago in astronomy, maybe there was a planet that had formed there that got smashed to bits. Turns out if you take all the stuff that's there and add it together, you're left with something that's just a tiny bit bigger than a quarter of our moon. So that's not really a planet-sized object. That's a very teeny tiny object, much smaller than even the smallest planet, Mercury. So half of that stuff is already gathered up together. That's the object series. I think it's closer to 40%, but it's a huge amount of the stuff of our asteroid belt, and it's just one teeny tiny object. So our asteroid belt, when you see it in movies or science fiction, places like Star Wars or Star Trek, it's full of objects swarming around. You've got to dodge, duck, dip, dive, and dodge to get around stuff. That's not the case. If you were standing on an asteroid looking out into space, you wouldn't even be able to see another asteroid. They're all too small and too far away. They would just be invisible. We had another question pop up. How many stars are there? Ooh, cool question. So, how many stars can we see in the sky? I'd say it depends a little bit on where you are. If you go outside in San Francisco on tonight, you won't see any stars because it's cloudy. If you go out on a clear night, you might see 100 stars. It's really not that many. That's because San Francisco suffers from something called light pollution. Light pollution can make it much harder to see stars. Well, if you went outside on a very dark place and you counted as many stars as you could over the course of a year, trying to observe as many stars as possible, the number we usually say is about 6,000 stars. There's about 6,000 stars that are clearly visible from San Francisco, naked, or excuse me, from Earth, naked eye, without the aid of a telescope or binoculars. But the thing is, that's stars we can clearly see and resolve with just our eyeball. If you've ever gone outside and looked at this hazy bright stuff that makes up the Milky Way, you're looking at stars. So let's see, you want to know more about galaxy and what's the Milky Way? That's a perfect question. So when we look at the bright stuff that we call the Milky Way, because it kind of looks like something bright spilled across the sky, what we're seeing is stars. Now, we don't see individual stars. This isn't part of that 6,000 number because we can't see an individual point of light. What we see is a bright glow. But imagine if I asked you how many blades of grass you've ever seen in your life, and you looked at a soccer field, would you count those as individual blades of grass? Or would you say, that's not a blade of grass, that's a soccer field? That's kind of the same problem we run into here. When you look at all this bright stuff, we're seeing stars. It's thousands and thousands, millions and millions of stars. Our Milky Way galaxy is made up of hundreds of billions of stars. Our galaxy is huge. So how many stars can we see? A couple thousand. How many stars could you see from orbit around planet Earth? A couple million. How many stars make up our galaxy, the Milky Way? Hundreds of billions. And if you live in the southern hemisphere and you can spot this thing over here and this thing over here, there are, I think, about 100 billion stars in each of those. That's the smaller and bigger, greater Magellanic Clouds. And if you really want to see a bunch of stars in one tiny patch of sky, you just have to look for the Andromeda Galaxy, because Andromeda has just as many stars as the Milky Way, except unlike our galaxy, you can see a lot of them at the same time. When you look at our galaxy, you can see nebulosity, which is this dark absorptive nebula. That's basically just gas and dust blocking our view. If it weren't for all this dark nebula, then we would be able to see the center of our galaxy. The problem is that all this dark stuff, this dark thready material, is blocking our view. Now, it would be pretty amazing to be able to see straight into the center of our galaxy and see all that light from all those ancient stars, but the dark stuff is beautiful too. If you look at constellations in the southern hemisphere, especially some of the indigenous preserved constellations, then they actually use that dark stuff to make pictures in the sky. There's features like the mama llama and the baby llama, the small fox. There's a bunch of really cool constellations that we just don't get in the northern hemisphere, because if you look at the sky we're most used to seeing, the dark stuff is harder to pick out. The only region where we get to see some dark stuff is in the southern sky near Sagittarius and Scorpius, the center of the galaxy we saw before. The part of the galaxy we see opposite that, over here, is the part with Orion in it. And while there are still some nebular features, things like the Orion Nebula right down here, Crab Nebula, you can see the Horsehead Nebula, a lot of stuff, they are brightest in infrared. So if you look at infrared pictures of this part of the sky, we get to see tons of nebula, but unfortunately, infrared doesn't make its way through Earth's atmosphere. Our atmosphere is very good at blocking it and absorbing it, I should say, so we don't get to see it. So infrared telescopes high up in the atmosphere or blasted off from space like Spitzer can do beautiful observations of that part of light in that part of the sky and see some truly amazing stuff. Check out some of the infrared all skies. Combine those words together in a Google search and you will see some amazing things. Okay, so we've been flying around pretty far from home for a little bit. Let's see if we can head back in to some of these planetary things. I've been orbiting Mars for a while, and it's always fun to zoom in on Mars. So I'm going to hang out on Mars until somebody gives me another idea of where we should be going next. Okay? Deal. So I talked about infrared. Mars is not an infrared planet, even though it does give off a little bit of infrared, I guess. It's just a red planet, regular old red. Why is it red? Well, the combination of iron and oxygen on the surface yields iron oxide, which we would call rust. When I think of rust here on planet Earth, I think about my old apartment in the western part of San Francisco where sea air got on metal and the water and salt combined with the metal to make rust, and it dismantled my bicycle. But that's not what's happening on Mars. Even though the final product, iron oxide, is basically the same, what we are seeing is carbon dioxide in the atmosphere combining with iron-rich dust on the surface, but this doesn't mean there's a lot of water or salt necessarily. All you need is oxidized iron to make rust. Now, when you think about that rusty surface, Mars is a very different color than Mercury because of that red dust. Underneath the red dust, we are always kind of shocked to see just how gray and dark Mars is, much like Mercury. When we talk about the substance that's covering that up, it is fleeting, it is ephemeral, it is blowing around the surface of Mars all the time. And sometimes in these giant planet spanning dust storms, it'll pick up a huge amount of dust and actually block our view of the surface. If you're a fan of the book The Martian, the first storm that knocks over the spaceship is a little bit fiction-y part of science fiction. But the second dust storm that makes it hard for his solar panels to absorb light, that is 100% science. And a very scary part of living on Mars. What if all of your power generation shut down? Okay, so we got a whole bunch of cool questions popping up. Let's see. Can we see Saturn's rings? Saturn. And can we attempt a landing on Europa? Sounds like we better head to Saturn. Let's see if Saturn is playing ball today. Heading on out there. When we get close to Saturn, we should be able to see first and foremost that beautiful ring. Man, is it cool looking. When you look at a telescope, or through a telescope here on planet Earth, pointed at Saturn, you often get a view maybe like this. You can see the ring, you can see some dark spots next to the planet itself, and you can see the planet. That's because from 1 billion miles away, which is about how far away Saturn is, we get to see very little of the fine details of Saturn. From orbit around it, like the Cassini mission, we get to see these the three-dimensional structures up close and personal and see some really beautiful stuff. The thing that always strikes me is just how thin that ring is. From the right angle, at special times of year, we pretty much get to see Saturn's rings disappear. That's awesome. It's kind of a lame thing to say, like when the rings disappear is the really cool moment, because seeing the rings is very special. But I will still say that seeing something change in space is always a special thing. So looking down at Saturn, we get to see that beautiful ring structure going around it. And we also get to see the bands on its surface. That is always a really cool thing to see. You can see light bands, dark bands. Light bands are usually called zones. Dark bands are called bands. But looking around on the surface of Saturn, there is a lot of variation, kind of like we would have expected to see on Jupiter, except my computer's being dumb. Okay. How are the rings formed? We suspect these rings, based on our evidence from the Cassini mission, are made of ice, probably overwhelmingly ice. There's some people that say there might still be a little bit of rock mixed in. So where did all this ice come from? How did it show up around Saturn? Well, it turns out Saturn has a ton of moons, has the most moons in the solar system, and most of those moons are icy. So it seems, based on some simple forensics, that a moon wandered too close and got pulverized. And when it got pulverized, it made that icy ring around Saturn. Now, that's a cool thing. Get it? Ice. But That ring is not stable. We think that over time, eventually the ring might fall into the surface of Saturn. However, how long that will take is something that scientists just cannot seem to agree on. It looks like Enceladus caught the Jupiter disease. I just see a flat gray surface, which is always a tricky thing because Enceladus is normally kind of smooth and light colored. Okay, let's see. What other questions we got? Can we visit the sun? Absolutely. And how did the sun form? Well, on our trip to the sun, I'm going to get us nice and lined up and actually take us backwards for a second. Because when the sun formed, we think the planets formed with it. So check this out. Long ago, we suspect that there was a big cloud of gas and dust. And that cloud of gas and dust was what would eventually become our solar system. In that dark cloud of gas and dust, a nebula, if you will, a lot like this nebula right over there, we see material beginning to pull together. Gravity is getting stuff closer and closer and squeezing it tighter and tighter. And as it gets squished in closer and closer, the middle part began to heat up. If it heats up too fast, it pushes all the outer stuff away and a star doesn't form. If it heats up too slow, there probably wasn't enough stuff. You just get a hot cloud. If they go in at just the right speed, just the right temperature, just the right amount of stuff, it forms a star. They could be big stars or little stars. Our sun is on the smaller side of things, but still a very common kind of star. And our sun clocks in at about 5,700 on the Kelvin scale, I say. I usually round it out to 6,000 just because that's the closest big number and it's easier for me to remember. But I think it's a little bit under that, if I recall correctly. But as our sun was forming, it had some leftover stuff trapped around it. That stuff was mostly hydrogen, but there was little bits of other things mixed in. And that stuff formed our planets. You might be thinking, well, if that stuff was mostly hydrogen, how did it form Earth, which is not mostly hydrogen? Turns out, if you added up all the planets of our solar system, Jupiter is the overwhelming majority. It's way more than half all by itself. So Jupiter is gigantic and it's mostly hydrogen. Saturn is the second biggest and it's mostly hydrogen. Everything else is just a tiny fraction of our solar system, but that's Mercury, Venus, Earth, Mars, the entire asteroid belt, the entire Kuiper belt, Uranus, and Neptune. The gas giants are gigantic in comparison. So as our solar system formed around our baby sun, we have the solar system as we know it. And how do we know this happened? Some of the biggest evidence is preserved in our asteroid and Kuiper belt, but also in the fact that our solar system is so flat. If you put our solar system on a plate, it wouldn't go too high above or too far below. It's a pretty flat solar system. And we think that the planets exist today where that disk of material was a long, long time ago. We had a question, is our sun moving? It absolutely is. Our sun is moving at super speed through our galaxy. Just like our planets are moving around the sun is moving around the center of the Milky Way. I don't think this is going to work, but I'm going to try it anyway. If we zoom back far enough, if I remembered to turn it on, there should be a model of our galaxy built in OpenSpace, and it's something you can do at home. I don't think it's going to work. Yeah, maybe. Yes! Ah! Cool. So let's check this out. I did remember to turn it on. When you look at our Milky Way galaxy, it kind of looks like it's spinning, right? Well, turns out it is. Our sun is right around here, and eventually we're going to make our way all the way around the center of our galaxy and back to the same spot. We call that one galactic year. So how long is one galactic year? It's about 200 million Earth years. That is a incredibly long time. So if you think about it, 200 million Earth years, that's 5 galactic years to 1 billion years. Our planet's about 4.5 billion years old. So our planet's about 20 galactic years old, maybe a little more. So in galactic years, our planet is about to turn 21. It promises to be an exciting birthday. But to give you a sense of perspective on how long a galactic year is, the dinosaurs lived on planet Earth still in this galactic year. That was less than 200 million years ago. So we're still not one full trip around our galaxy since the dinosaurs died. As we zoom in, you can start to imagine our little planet Earth zooming through space, hanging out with all the stars next to us, traveling as kind of a unit together. And as we are moving through space, Those constellations we see and we're used to change and bend over time. As we zoom through the Milky Way, there's no reason to think that the stars would hold in perfect formation around us. We're all moving. And if you want to find out some more amazing stuff about these moving stars, how our star is moving, and how we learned about these super cool things, you're going to want to tune in this Friday because we have Dr. Jackie Faraday from the American Museum of Natural History telling us all about the Gaia spacecraft. Gaia has been studying the stars it can see and very carefully learning about their motion over time and has built a beautiful, gigantic picture of how the stars around us are changing and what we can learn about that. So, by all means, please tune in. It is so cool. Okay, let's see if we got any other questions popping up. How hot is Mercury, as it's the closest one to the sun? Oh, Jack, we had another cool one too. So, Mercury would be the hottest planet, right? Because it's the closest one to the sun. There's a very simple logic there. When you're close to a campfire, you get very warm. If you move farther away from a campfire, you get very cold. But here's the puzzle. When you are standing next to a campfire, imagine on a very cold night, your front half, the part that's facing the campfire, gets warm. But if you've sat by a campfire for as long as I have, you'll start to notice your back half can get really chilly. So how do you fix that? You put on more clothes. You wrap yourself in a blanket and then you face the fire. Well, Mercury doesn't have a blanket. Mercury has one very hot half and one very cold half. I think the part of Mercury that faces the sun at noon might get slightly hotter than the next planet, Venus. But in general, we say Venus is the hottest planet overall because Venus is wrapped in that incredible thick atmosphere. Because of that atmosphere, it's like Venus is wrapped in blankets. It spreads heat around its surface. So all parts of Venus are around 900 degrees Fahrenheit, as opposed to Mercury, where one half is very hot, the other half is very cold. Okay, we are getting a little short on time, but I think we got time for one last trip out to Neptune. Let's check out Neptune and its toxic environment. Normally, when people are making jokes about poisonous gases, they focus on Uranus, but Neptune is also a place with a pretty different atmosphere than our very own planet Earth, which can come as kind of a shock because when we see this line, it's blue. When we look at the surface of Neptune, it's also blue. Couldn't this be a beautiful ocean world just like planet Earth? No. We've done some analysis of the clouds that we're seeing as this top layer. That's where the blue is coming from, not a blue ocean underneath. The clouds themselves are blue. And let me tell you, you don't want to breathe anything that's a different color than what you're used to breathing because it's not going to work out well. We need nitrogen with bits of oxygen, some carbon, a lot of other gases here on planet Earth. If you try and breathe something that looks blue to us, it's not going to work out well. So when we look at Neptune, we are seeing a completely different kind of world. As Jupiter is very different than Mercury, Neptune is very different than Earth. Neptune is what we call an ice giant. So ice giants are probably a strange combination of solid, liquid, and gas. They've got an atmosphere on the outside and then a liquid slushy material underneath that that's a little solid and a little liquid. It is a completely different kind of planet to our own. So I hope one day we get to send some missions out there to do some more in-depth study of Uranus, of Neptune, because they are places that are just so different than the inner worlds of our solar system. And as we look to planets around other stars, we've begun to discover that there are tons and tons of worlds very similar to Uranus and Neptune. They seem to be a lot more common than small rocky planets. At least we're finding more of them, but that could be a function of the fact that they're bigger and maybe block more light. So we're going to start heading our way back in towards planet Earth. And as we do, I would like to thank all of you for joining me here for our virtual tour of outer space. I hope all of you learned something. If you did and you want to share it, throw it in the comments. If I was able to share a new fact for you. If I didn't share a new fact for you and you're still aching for something that you haven't heard before, by all means, tune in next week. We will be doing another virtual tour of outer space. I will see if I can fix Jupiter, and we're happy to take any suggestions about a place you think might be a really cool spot to check out. So with that, on behalf of myself, Morrison Planetarium, the American Museum of Natural History, and our friends at OpenSpace, thank you for joining us here for our virtual tour of outer space. If you have questions or comments, throw them in the chat. We will be happy to try and answer them a little later. On behalf of myself and my museum, thank you all for joining us. We really appreciate your online attention. It is great for us to be able to give our planetarium shows still, but stay home, stay happy, stay healthy, and we hope to see you soon.